Tahniah! Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia. Sebuah inisiatif E-Didik Malaysia dan Kelab Guru Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hai. Okay, Assalamualaikum dan selamat sejahtera. Okay, hai kepada semua guru, ibu bapa yang dihormati dan para pelajar yang cikgu kasihi sekalian. Okay, selamat datang ke Pusat Tuisyen YouTuber AYU, usaha sama E-Didik Malaysia dan Kelab Guru Malaysia. Ingat hashtag, bermula percuma, selamanya percuma. Untuk mendapatkan keberkatan kelas kita pada petang ini, bagi yang beragama Islam, marilah kita sama-sama memulakan kelas dengan membaca umum kitab Al-Fatihah, dan kepada yang bukan beragama Islam, kita bertafakur sejenak. Al-Fatihah. Amin, amin ya rabbal alamin. Okey, apa khabar semua? Apa khabar para pelajar yang cikgu kasihi sekalian? Okay, harap semuanya berada dalam keadaan baik dan bersedia untuk meneruskan kelas kita pada petang ini. Okey, jangan lupa kita isikan masa dengan tuition online percuma. Okay, cikgu percaya pelajar-pelajar dah tak sabar untuk mengikuti kelas fizik Prayu khusus untuk STPM dan matrikulasi ini. Okay, sebelum tu, cikgu perkenalkan diri dahulu. Okay, nama cikgu, Cikgu Hafsah Ayu binti Muhammad Arifin dari PTE SMK Sultan Sulaiman, Kuala Terengganu selaku moderator pada petang ini. Okay, bersama cikgu di studio pada petang ini ialah Teacher Im. Okay, Teacher Im, hai Teacher Im dari Kolej Tingkatan 6 Tapah selaku host dan juga Cikgu Zanaria. Hai Cikgu Zanaria, bekas guru dari SMK Tempuan Durrah Negeri Sembilan sebagai pemerhati dan juga presenter kita pada hari ini iaitu Madam Rosmaya. Hello Madam Rosmaya. Okay, dari SMK Yu Hua Kajang Selangor. Okay, pada petang ini, kita bersiaran secara langsung dari channel Madam Rosmaya. Sesiapa yang belum subscribe beliau, silalah tekan butang subscribe sebagai tanda sokongan kepada Madam Rosmaya. Okay, tajuk yang akan disampaikan oleh Madam Rosmaya pada petang ini ialah Hall Effect. Okay, diharap para pelajar dan para penonton dialu-alukan untuk mempelajari topik ini. Okay, kelas ini akan berlangsung selama lebih kurang 1 jam. Sebelum kita teruskan kelas, suka cikgu ingatkan semua pelajar dan penonton yang ingin menghantar komen agar menggunakan bahasa yang sopan dan gambar profil yang bersesuaian untuk tontonan umum. Cikgu percaya semua yang hadir kelas pada petang ini merupakan pelajar-pelajar yang cemerlang dan marilah kita tunjukkan disiplin yang terbaik. Okey, sila fokus pada isi pelajaran yang akan disampaikan oleh Madam Rosmaya dan menggunakan ruang chat untuk menjawab soalan atau jika ada soalan yang hendak diajukan. Pada akhir siaran ini, link e-sijil akan diberikan bersama kod akses. Pastikan anda menggunakan email e-didik sahaja. Dan ada satu perkara baru, ada mata ganjaran kredit kerana mengikuti kelas tuition AYU. Anda boleh menebusnya dengan hadiah istimewa. Anda perlu memohon ID e-didik junior terlebih dahulu sebelum mengisi borang klaim kredit. Link untuk memohon ID e-didik junior diberi semasa kelas berjalan nanti. Anda semua boleh mengisi borang klaim kredit apabila diberi link di akhir kelas. Kod untuk klaim kredit ada 5 digit. Okey, 5 digit tapi cikgu akan berikan sebanyak 4 kali. Okey, pastikan anda mencatat dalam kertas. Untuk meningkatkan integriti, diminta anda jangan share kod kelas yang diberi. Okey, nombor kod yang pertama. Okey, nombor kod yang pertama ialah A1. A1. Okey, tanpa membuang masa lagi, cikgu serahkan kelas kita kepada Madam Rosmaya. Okey, dipersilakan Madam.
Okay, hi everyone. I am Madam Rosmaya. Thank you to our moderator, Puan Hapsayu. To those who are new here, okay, maybe you don't know me yet. I am Form 6 teacher at SMJKU Hua Kajang. So I actually come from Kedah, but stay at Kajang for so many years already. I have 28 years experience in teaching and got my Bachelor Science with honours in physics from UKM. So after got married, I decided to continue my profession as a teacher because I love teaching so much. Yeah? Okay, so without further delay, so let us continue with our discussion today. So do you see my presentation? Okay. Okay, I also would like to introduce the team in Academy YouTuber. Okay, our team. So physics team, okay, lead by me, Madam Rosmaya. I'm Madam Rosmaya, and we have also teacher AYU here with us as a moderator. Okay, not here is teacher Su, teacher Suhaya, teacher Nun, and teacher Rashida. Okay, then you also have maths team, and the teacher lead this team is teacher Im, on top of me. Okay, yes, on top of me. And then also we have teacher Zanaria at the bottom of the screen. Okay, teacher Zanaria, and another teacher is teacher Eileen. Okay, then we have biology team also lead by Cikgu Faiza, and we have chemistry team lead by Cikgu Shahnon, and we have perakaunan dan ekonomi lead by Madam Fizi. Okay. So, okay, so what is the objective of our discussion for today? So today we are going to discuss on topic magnetic field, and the subtopic is Hall effect. Okay, so by the end of this discussion, so you will be able to describe the Hall effect and calculate the Hall EMF across a current carrying conductor, okay, using this formula. We also are going to derive this formula, the Hall voltage. VH is the Hall voltage, equals to BI per NET. So B is a magnetic field, I is the current, N is the number of charge carrier, and E electron charge, and the T, time taken. Okay. Okay. So in the previous discussion, we have derived a formula of a magnetic field for a straight wire, a circular coil, and a solenoid, if you remember our previous discussion. So is there any specific device that we can use to directly measure the magnitude of a magnetic field? So how are you going to measure a magnetic field strength? So in primary school or secondary school, okay, you use a compass. Okay, you use a compass to determine the direction of magnetic field, but it doesn't give you the magnitude of the magnetic field. So the magnitude of the magnetic field, if we measure, if in the previous lesson, if you realize the unit got Tesla, right? The unit is Tesla. Okay, so one of the device that we use to measure the magnetic field is called Gauss meter, or Tesla meter here. This is Gauss meter or Tesla meter. Okay, so one of the component, if you see here, okay, is the Hall probe, which is put in the magnetic area, then the reading of the magnetic field will be displayed by this component. This component, okay, this is the meter, okay. So if you can read there 136, this means the unit is Tesla, okay. So this is the Hall probe we use. Okay, so now what is Hall effect? What is Hall effect? So Hall effect is a phenomenon that occurs when a conductor or semiconductor. So the Hall probe just now, the Hall probe can be a conductor or semiconductor. So it's placed in the magnetic field. Okay. So the phenomenon that occurs when the conductor or semiconductor placed in the magnetic field. And what happens next is a voltage is applied through the material perpendicular to the magnetic field. Okay. So this is the probe. Actually, the metal here maybe conductor or metal example, semiconductor put here. So this is the shown in the animation here. The magnet, you can measure the magnetic field here. So when you connect to the voltmeter here, so what happened? There's a reading. So we will discuss in detail how this happened. Okay. So while this voltage induces a current flow along the electric field direction, okay, the charge carrier also experience a magnetic deflection from their path. This is the charge. Electric current is a flow of charge, the electron flow. So the charge carrier in this example is the electron. So it experiences a magnetic deflection from their path. So this results a separation of positive and negative charge carrier. Okay, and thus the generation of an electric field perpendicular to the direction of current flow. Okay, maybe by this statement, you still cannot see what really happened actually. So we go to the next slide. Okay, so I divide the phenomenon, okay, to explain the phenomenon. So I divide into 4 easier steps for you. Okay, 4 steps of Hall effect. So the first step, okay, the metal or the probe just now can be conductor or semiconductor. So let's say it's a conductor here. So let's say the current flow is this way. This is the first step. So the next explanation, imagine you can see in the microscopic view, you can see the electron flow. So the flow of current, actually the flow of electron in this opposite direction. This one you've learned in primary school or secondary school. So the flow of current is this way. Okay. So represent by the red ball there, the small ball there. Okay. Now next we apply a magnetic field. Okay. Upward direction, in the upward direction. Okay. So using the Fleming's left hand rule, so B is upward direction. Here shows by the forefinger. Okay, and then direction of current, electron flow this way. So direction of current this way. So follow the direction of current, the middle finger, okay, into the screen. Okay, if you see this as a 2D dimension, two-dimension diagram. So the electric current is into the screen. So these 3 fingers must perpendicular to each other. And lastly, you see that the thumb shows direction to the right side, to the right side. So what happened to the electrons here? Okay, so it will experience a force to the right side. So all will accumulate at one side of the conductor. This is conductor. So it will accumulate one side of the conductor. Okay, on the right side in our diagram here, on the right side. Okay, so the force. Okay, so the last step is what happened as the charge, as the electron accumulate here at one side, so it become negatively charged here on the one side. So the other side will be positively charged. So this, what happened is electric field, okay, exists because of we have one positive side, the other one is negative, positive charge, the other one is negatively charged. So we have electric field. Okay, in this direction, So to the right, okay, to the right. So because of we have electric field, okay, so when we connect a wire across here, the two surface, these two surface. So what happened? There is a reading in the voltmeter. We connect a voltmeter across the two surface here. So what happened? We have a reading in the voltage here. So we call this voltage reading as a Hall voltage. Okay, Hall voltage. So this is where the Hall voltage come from. So this is called the phenomenon of Hall effect. Okay, so this is another diagram to show you what really happened actually. So the flow of electron here, this is magnetic field north to south. This one is downward actually. Just now this is upward. So let's do this one. Okay, so the north to south, so that means the B is downward. Just now B upward, right? So north to south, the B is downward, shown by the forefinger here. The current, look at the current here, is into the screen. Okay, so lastly, the thumb shows to the right. The force, magnetic force to the right. So that's why the electron here accumulate at one side, deflect to one side because of this force, magnetic force. So this is another diagram. So when we connect these two sides, that this side is a negatively charged, so the other side will become positive. So what happened? There's an electric field produced. So when we connect a current, when we complete the circuit outside here, or we connect, we connect a wire, okay, circuit across these two sides. So what happened? We can have a reading in the voltmeter here. Okay. Okay, next slide. So one of the use of Hall effect is we can determine the sign of charge carriers in the semiconductor. So remember that the metal just now, the what we call the probe just now can be used as conductor or semiconductor. So if we use semiconductor, we can determine the sign of the charge carrier in the semiconductor. So we refresh or we recall to what we've learned before in Form 4, Form 5. So there are two types of semiconductor. Okay. We have intrinsic semiconductor and extrinsic semiconductor. If you can remember, we've learned before in the secondary school. So for intrinsic semiconductor, example is a germanium, silicon. Intrinsic means the pure form of semiconductor. So the number of the charge carrier electron is equals to the number of holes. Okay, the charge carrier is electron equals to the number of holes. So for the N-type of for the extrinsic semiconductor, there are two types. We have N-type and P-type. So depends on the impurity. What in the impurity in the semiconductor we dope in, doping in. So for N-type, the number of charge carrier is electron is larger than the holes. Whereas for the P-type, the number of charge carrier hole is larger than the electron. So if you can imagine what we've learned in Form 4, Form 5, okay, this is the dope semiconductor. This is the intrinsic. So this is the extrinsic. We dope with the, let's say phosphorus. You can dope with phosphorus, okay, antimony, or any AS, forgot already what this is. So if we dope it with phosphorus, so we get N-type semiconductor. So if we dope the other semiconductor here with boron, so we have P-type semiconductor. So it depends on the what we dope in the semiconductor. Okay, so the impurity for this one and type, the impurity atoms added, so provide extra electrons in the structure here and are called donor atom. So that's why the electrons are the majority charge carrier and holes are the minority charge carriers. But whereas for the P-type, the impurity atoms added create vacancies of electron. So example here, holes here. So in the structure, this is called acceptor atoms. So the holes are the majority charge carrier and electrons are minority carriers. So this is what we've learned before. So to relate what we are going to discuss today is the Hall effect. Okay, so we can determine the N-type and the P-type semiconductor, okay, using Hall effect. Okay, so now go back to the Hall effect. Okay, so we are going to discuss specifically N-type and the P-type. Okay, we start with the N-type. This is the N-type. So N-type, remember, the charge carrier mostly is the electron. is the electron. Okay, so the electron now flow through here. The what we call, we imagine it. We can imagine the flow, because number of charge carrier for n type is mostly is an electron. So we can imagine as the electron flow. So to determine the direction of force, where the electron will deflect, so we use Fleming's left hand rule. Okay, so let's say the B is upward, the B is upward, magnetic field is upward. So the current is this way. Look at the direction of current given. So it out of the screen. So then the thumb shows direction to the left. Magnetic force is to the left. Okay, this is the magnetic force to the left. So what happened? The electron, will accumulate to one side, means left side of the semiconductor here. This is semiconductor. So the charge carriers experience a magnetic deflection from their path, which is at the left side. Okay, deflect to the left side. So therefore, on the right side, this is an animation to show, like this one. Okay, so that means on the other side will become positively charged. Positively charged. One side negative, so the other side will be positively charged. So this create a electric field. Electric field. So this result a separation of positive and negative charge carrier. So thus generation of an electric field perpendicular to the direction of the current flow. So which means direction of electric field is from positive to negative. But the electric force is this way, to the right, correct, to the right, because the charge carrier is electron. Remember, for n type, the charge carrier is electron. So electric field is this way because the electron attract to the positive sides here. Okay. Okay, so this is how to imagine. So refer to this diagram. So the current flow this way. Let's say from diagram just now we look from the bottom. We look from the bottom. So the magnetic field is into the screen. Cross means the magnetic field is into the screen. So the current flow this way, and this is the charge carrier. Oh, this is the P type actually. The diagram here shows the P type because P type is the holes is the most charge carrier in the P type. So you can just imagine it's a positive holes or positive charge flow here. So that means the positive. Now we go to the P type here. Okay, this is the 2D diagram. This is the 3D diagram. So look at the positive charge here. Compare with the 2D diagram. Okay, the flow of electron this way. So the flow of positive charge also this way. So using Fleming's left hand rule. So the B is still upward. Upward. Okay, then the current is this way out of the screen. So the force is this way. Okay, force of this way. So the because of this is P type. So the positive charge will deflect to the right because it's the P type. So the positive charge will deflect to the left. Left. Okay, this is left side. So the positive charge will deflect, or the holes actually deflect to the left, to the left. So this side, left side will become positively charged. So the charge carriers experience a magnetic deflection. Okay, this here the hole accumulate here. So the other side will become negatively charged. Okay, so this result a separation of positive and negative. Compare with just now, because this is the P type, so positive charge will accumulate here. Negative, the other side will become negatively charged. Okay, so again, the generation of an electric field perpendicular to the direction of the current flow. So now electric field is which way? To the right, to the right, from positive to negative. But the electric force also to the right, because the P type is the charge carrier is the holes, positive. So that means it's attract to the negative side. So therefore the electric field, the electric force, this is electric force. So therefore the electric force is this way. Okay, now? Okay, now compare the both just now. I repeat. Okay, just now we go slow motion. So now compare these two. Remember that n-type, you can assume, not assume, actually the charge carrier more is the electron. Okay, so if the current flow here, so the electron flow oppositely here. So what happened? Using the Fleming's left-hand rule, for both, actually for both, electric field is crossed here into the screen, okay, for both. And the current both is this way to the right, okay, so current is this way to the right. So both electron for n-type and p-type, the charge carrier will experience the magnetic force upward, upward. So that's why you can see how the electron for the n-type accumulate on top. So here the p-type is the whole, so the charge carrier is the whole or positive charge. So also accumulate on top here. Okay, easy to describe because this is 2D diagram. So both accumulate on top using Fleming's left-hand rule. So the magnetic force experienced by both n-type and p-type by the charge carrier, that's why they deflect at the top, at the top. Okay, you can see the difference. Okay, so now we continue. The code. The code I forgot. Code mentioned already, right? Mentioned already lah. Cikgu teacher Aileen, right?
Kod yang
digit.
Kod yang kedua.
Kod yang kedua. Kod yang kedua. Kod yang kedua belum lagi kan? Nombor 5.
Yes. Nombor 5. Okay, number 5 Okay, so now we continue. Okay. So now after some time, what happened? After some time, so the electrons will reach the equilibrium state. So it keep on actually accumulates on top, for whether it is n-type semiconductor or the p-type semiconductor. So after some time, so the flow will becomes equilibrium. So when the electrons, or here in this the bottom picture is the p-type, so the positive charge or the holes becomes equilibrium. So the electrons or the holes is no longer deflected. So you can see the flow of electron. You can see or not? So it no more deflected. So it just flow straight across the hole, the probe here, the semiconductor here. Also the same as the holes. Okay, after some time, when the equilibrium state reach, or in other words, we say in a steady state. Okay, in a steady state. So now we can next we are going to derive the formula for the Hall voltage at when the steady state occur. Okay, when the steady state occur. So when the steady state occur, what happened? The magnetic force is equals to the electric force. Okay, magnetic force equals to the electric force. So that's why the charge carrier in n-type is the electron. Okay, in the p-type is the holes. So it no more deflection occur. Because balance, magnetic force and the electric force balance, so they are equals with each other. So we can write as Fm equals to Fe. So Fm represent magnetic force and Fe represent electric force. Okay, so shown here. Okay, I draw here so that you can see. From the Fleming's left-hand rule, Fm is upward, right? So Fe is downward. So for the first picture, first diagram here, Fe is downward because the electron, okay, repel or attract to the positive side here, or repel the negative side top here. So that's why electric force is downward. Whereas for the p-type, charge carrier is the positive or holes, so it's attract to the negative side or repel the positive side on top here. So again, the electric field also downward. Okay, both cases are the same. So Fm equals to Fe. So understand? Any problem? You can just write there in the chat box. If you want to ask anything, can just write there in the chat box. Okay, so the Hall probe in this case,
Madam,
yeah.
okay, rasanya elok kita berehat sekejap.
Okay, so
Kita berehat sekejap untuk bagi laluan kepada iklan. Sementara kita bagi pelajar ni boleh refresh balik apa yang diorang pelajari hari ni. Okay, kita iklan sekejap.
Berita baik untuk semua. Kini Akademi YouTuber memperkenalkan sistem mata gancaran kredit AYU untuk dikumpul. Jom ikuti kelas tuition live AYU untuk mengumpul kredit AYU dan berpeluang menebus hadiah-hadiah yang menarik. Hadiah bernilai lebih RM10,000 disediakan secara percuma untuk pelajar seluruh Malaysia. Apa tunggu lagi? Tebus ganjaran hebat ini sekarang. Layari www.academyyoutuber.com untuk maklumat lanjut.
Okay, welcome back.
Okay, boleh teruskan.
Okay, so I continue with our discussion today. So now look at this question. Okay, so the Hall probe is placed near one end of a solenoid like this one. This is a solenoid. So this is the Hall probe as shown in the diagram here. So the Hall probe now is rotated about the axis XY. Okay, XY is rotated. So why the magnitude of the Hall voltage varies? So why the magnitude of the Hall voltage varies as the Hall probe here is rotated? So anyone can or not? Can answer this or not? So why the reading here varies as you rotated the Hall voltage? Okay, let's try answer this question. Okay, why the magnitude of Hall voltage varies? What do you think? Compare, you imagine the way we put the magnet just now, the magnetic field, in which way? But this one we rotate the magnetic, the what you call this magnet. So what happened? Okay, I think we better discuss because this one is new to you all. But those who can answer, actually very good. Okay, so we discuss this one. Okay, so the Hall voltage actually depends on the angle between the magnetic field and the plane of the probe. Remember this. Hall voltage depends on the angle between the magnetic field and the plane of the probe. So you must put the position, choose the best position so that you get the value, the high value of the highest value of the voltage here, the Hall voltage given. Okay, so the Hall voltage reaches maximum when the field is perpendicular to the probe. So like we discussed just now, we put the probe just now, okay, the semiconductor or either semiconductor or conductor perpendicular to the magnetic field. Okay, so the Hall voltage will become zero when the field is parallel to the probe. So it depends on the angle. So that's why the magnitude of the Hall voltage varies when you rotate this Hall probe. Okay, hopefully you understand that. Okay, the position of the Hall probe is very important to get the highest value of the Hall voltage. So that is the conclusion. Okay, now we are going to derive the formula just now. Hall voltage is given by BI per NET. I repeat again, B is the magnetic field, I is the current, N is the number of charge carrier. So E is the electron charge and T is the time thickness. Actually thickness. I see just now time. Okay, so don't get confused. The T for time and the thickness. T is the thickness actually. Thickness for the conductor or semiconductor used here. Okay, the probe here. Okay, so continue from the force of electron. Force on the electron is equals to QE. So the Q is electron. So EE, E is the electric field. Okay, because the electron this way, the electric field, the electric force is this way because it they repel each other to the electron that accumulate one side here. So the electron still flow here. So it's repel each other. So that's why electric force is to the right side, to the right side. Okay, so when remember just now we also discussed when the electrons in equilibrium. So what happened? The electrons are no longer deflected. So it goes straight from one end here to the other end of the conductor, this conductor or semiconductor. So when you put the voltmeter across these two sides, so what happened? It gives you the reading of the Hall voltage. Okay, so this force direction to the right, the electric force, and is equal to the magnetic field. So we can write as EE equals to EVB. EVB is the magnetic force. Okay, so EVB is the magnetic force. Remember the previous lesson, force is equals to QBV. So in this case, the charge is E. So we can cancel out the E. So we get E equals to VB. Okay, so now electric field here, how to relate with the Hall voltage here. Also in the first chapter for semester 2, you've learned that E equals to V per D. So in this case, the Hall voltage we substitute into here. So the voltage across here, the what you call this, the conductor or semiconductor. Okay, so the thickness of the the width of the semiconductor here is D. So it's VH per D. Because we connect the voltmeter here across the two sides here. So we use the distance between the two electric field produced because one side is positively charged, the other side become negatively charged. So therefore, the distance between them is D. So VH per D. Okay, next, we cross multiply. So we get VH Hall voltage equals to VBD. Okay, VBD. Okay, next, the V, we use formula I equals to NEVA, INEVA, from the chapter 14 or 13, I'm not mistaken. We discussed before, okay, in that chapter, direct current chapter. So we derive this formula already, I equals to NEVA. So V is I per NEA. So we substitute into here. Okay, we substitute into here. So I per NEA. Then A is the cross-sectional area. So the current flow this way, right? So the cross-sectional area will be T times D. T times D, thickness times the width. So T is the thickness of the conductor times the width of the conductor here. So T times D. Okay. So next we can cancel out D. So the equations become VH equals to BI per NET. Okay, so we derive the formula for the Hall voltage. Okay, so done for the derivation. So next, from the VH equals to BI NET. Okay, so from this formula, we can see clearly that the use of Hall effect is to measure, you can use it to measure the magnetic flux density B. Okay, so Hall voltage is directly proportional to B if the current made constant N, E and T, thickness all constant. So Hall voltage directly proportional to B. So that's why we can create a device like this to measure the magnetic field. Okay. So the advantage of using Hall probe to measure the magnetic flux density BR is a small size, make it especially suitable for measuring the magnetic flux at small isolated places. Example, the solenoid, right? Solenoid is small, right? So it can, there's small isolated places actually in between or inside the solenoid. So you can use the Hall probe, right, to measure. the magnetic field, and also it is very sensitive and is therefore is suitable for measuring fields whose flux density varies with time, such as the magnetic field set up in the solenoid when alternating current is flowing. Okay, so this is two advantages using using Hall effect to measure the magnetic flux density in this device. Okay, next slide. Okay, try this one. So Hall effect is the effect that, okay, can you all remember what we've discussed in the previous, in the early discussion? So can you answer this or not to check your understanding? So Hall effect, what is Hall effect actually? So A, B or C? So A is when a current carrying conductor is placed perpendicularly uniform magnetic field. B, voltage produced when a current conductor is placed perpendicular uniform magnetic field. And C, when a conductor is placed in magnetic field. So looks like the similar answer. So but which one is the best? What is Hall effect actually? We have discussed before. So anyone can try to answer? Can write there in the chat box. So which one is the best answer? Okay, so Vinay, you say B, question mark. So that's mean you not sure. So Chia Hao Seng, Kao Min, B, Valamati B, P. Most of you say that B, say that B. So the answer actually A, it's not B. So why? A, when a current carrying conductor, remember the current carrying conductor like a conductor just now or the semiconductor must be placed perpendicularly uniform magnetic field, perpendicular to the uniform magnetic field. So this is where the Hall effects occur, the phenomenon occur. Whereas B is the voltage produced when a current conductor is placed perpendicular uniform magnetic field. So the voltage produced here is where actually? So it doesn't mention. If it mentioned here the voltage across which is the two side actually, not for the circuit just now. I go back to the here you see. So the whole voltage occur on the other side here of the other two side, whereas the current flow here. So the voltage is not the voltage across these 2 points. Okay, across the conductor actually. The voltage here is the whole voltage across the other two sides. So this is where you may actually every student confused with the whole voltage. It is measured which across which side actually. So the whole voltage is measured across the other two sides of the current carrying conductor. Either it's a conductor or the semiconductor. Can see or not why we cannot accept the answer B? Okay. So because it doesn't mention the voltage produced when a current conductor is placed perpendicular. So it doesn't mention where the voltage is measured. Understand? So it's not B, the answer. So C for sure lah is wrong when a conductor is placed in magnetic field. So the best is the A. Okay, when the current carrying conductor is placed perpendicularly, the word perpendicular is very important, uniform magnetic field, because it gives you the highest value of the whole voltage. Okay, hopefully you know where you go wrong. Okay, it's a tricky question actually, right? Okay, so try next. Next question. Yes, any the code the third code I think before we go to question 2. Okay, cikgu teacher Hapsayu.
Number 0.
Okay, 0 the code. Okay, 0 the third code. Okay, thank you teacher.
Okay.
Okay, so go back to the question 2. Okay, typical value of hall voltage produced is about, okay, what do you think the value? A few volts or few nanovolts, few kilovolts or few millivolts? What do you think? Okay, so many of you answer C. Yeah, I bet. It's the correct answer, C. Yeah? So good. That is the correct answer, C. Okay. Dylan Yap, who else? Balamati, Sinwe, Loga, Chai Teng Xuan, Chi Hao Seng. Okay. So the answer is correct. Few millivolts. So cannot view few kilovolts. So very large. Volt is very large. So it's actually about few millivolts. Nanovolt is too small. Okay, so next. This one to test whether you can remember or not the formula. Okay, choose the correct formula for hall voltage. So before we continue with the calculation part. So choose the correct formula for hall voltage in terms of thickness, T. Okay, the charge we use Q. Capital letter Q, actually small letter, typing error here. Q, small letter Q. And then current I. Okay, current I, number of charge density N. Okay, and the magnetic field strength B. So which one is the answer? Okay, anyone? Can remember or not the formula? Okay, Gaumin, Gaumin Chai, or Chai Gaumin, Chai Teng Xuan, okay, B, okay, very good. Okay, so the answer is correct, B, Dylan Yap and who, our friends, our students here, all answer B. E, Y, Wong Chai and E, oh, got E also. Remember the formula is BI per NET. In this case is Q because no square. E got square. Maybe you didn't realize the square there, Wong Chayan, okay? So no square. The formula is BHB. The answer is B, correct? Okay, good. So you can still remember the formula BI per NET. I prefer to memorize it as BNet. BNet, easy to memorize. So choose the way that you can have the easy to memorize the arrangement of the equation. So I prefer to memorize as BI per NET. BNet, right? No square, no square. Yeah, E got square. C got square. So BNet only. Okay, now it's time to calculate. Okay, so you can calculate put together. Here we read first. In a Hall effect experiment, a current of 0.25 ampere is sent through a metal strip having thickness 0.2 millimeter and width 5 millimeter. So the Hall voltage is found to be 0.15 millivolt. So when a magnetic field of 1 times 10 to the power of -4 Tesla is used. So what is the carrier concentration? And then what is the drift velocity of carriers? So what is meant by carrier concentration? So this is another way actually to ask the N, number of charge carrier density. So N actually, A is to find N. So some books say carrier concentration. It has the same meaning as number of charge density. Okay, so can try to calculate the N actually for A question. Then you can continue to calculate the drift velocity of the carriers. Okay, this is metal strip. Sometimes they can ask you actually what kind of charge carrier. Mention here a metal strip. Okay, but they didn't ask here in the question. Okay, I give you a few seconds. Okay, it's very easy actually, just to test you whether you remember the formula or not. What is the formula just now? V, Hall voltage, equals to BI per NET, BNet. V equals to BNet. Okay, anyone got the answer already? You can write there in the chat box. Okay, I'm waiting here. So N, remember, the question asks for N. Carrier concentration means number of charge density. Number of charge density. So the formula B net. BI per NET. Magnetic field is given. Okay, current is given 0.25 ampere. E, what is E? E is the electron charge. In metal, this is the keyword here, metal. Metal means the charge here is electron. So what is the charge for electron? You should memorize there. Or given in the your calculator also got the value of E, 1.6 times 10 to the power of negative 19. 1.6 times 10 to the power of negative 19. You've done so many exercise already from chapter 4, chapter before. So you should know the E value, 1.6 times 10 to the power of negative 19. Okay, then the whole voltage here 0.15 millivolt. The thickness here T 0.2 millimeter. Okay, anyone? Are you calculating? Still no answer there. I can see in the chat box no answer yet. Do you find it's hard? Remember the formula. Okay, so if no one answer there, so we continue. This is the formula. While I'm explaining here, if you got the same answer or you got answer already, you can write there in the chat box. Okay, so we have the answer from, okay, so you take times to answer. Okay, so most of you get 5.21 times 10 to the power of 2. 10 to the power of 21 meter per meter cube. Okay, charge density, right? So per meter cube, number of charge per meter cube. Okay, let's check your answer. Okay, so to find N, you rearrange the equation here. N becomes BI per whole voltage times ET. So you substitute the values of B, then the I. Don't forget to convert to the SI unit, millivolts. So convert to volt times 10 to the power negative 3. And the electron charge is 1.6 times 10 to the power negative 19, and the thickness is 0.2 millimeter. Convert to meter. So you get 1.04 times 10 to the power of 25. My answer is wrong or your answer? I also haven't checked. I didn't check this one. But the substitution here is all correct. If you use the correct substitution here, then you will get the answer. Okay, per meter cube. So I didn't put the unit. The unit here is per meter cube. Okay, so most of you get this answer. Okay, so I got 1.04 times 10 to the 25. Check where you go wrong. So any problem can write there in the chat box. Okay, now the drift velocity. The drift velocity. So the drift velocity V. Okay, we are going to determine V. So we know N. So this one must relate with the previous chapter, not in this chapter. So they can combine the 2 or 3 chapters in one question. So we use I equals to NEVA. I like to memorize this as I never. Easy to memorize, I never. So NEVA, so you substitute the values just now N into here and with the rest of the given the given information. So I is 0.25, N is just now 1.04 times 10 to the power 25. E is 1.6 times 10 to the power negative 19, and the area. Okay, so the area must be very careful. So the thickness is 0.2 millimeter. So the width of the metal stripe is 5 millimeter. So 0.2 convert to meter. Then 5 millimeter also convert to meter. So you get this answer. So the V is 0.15 meter per second. You all get 0.15 meter per second or not? So those you all only answer A, question A only. B didn't write there. It's okay if you got same answer, you can get there. And if got problem, because I also didn't calculate this one, didn't calculate this whether correct we got this answer or not. So if you calculate this, you got this answer. So it's correct lah. So you substitute this value into the next for question B. You get this answer 0.15 meter per second. Okay, so we go to the next question. So ready for the next question? Looks like no question from you in the chat box there. So we go to the next question. Okay, question 5. Question 5. Okay, we read together the question first. A thin slice of semiconductor wafer, okay, because in the shape of wafer, so that's why we call this semiconductor wafer, has dimension of 10 millimeter times 3 millimeter times 1 millimeter. So be careful which side the current flow. So given that 10 millimeter, which way? The length of the semiconductor. Then 3 millimeter, which one? Millimeter is the width. The width here, so the current flow this way, the width of the semiconductor, and times 1 millimeter. So 1 millimeter, the thickness, means 1 millimeter is the thickness of the semiconductor. Okay, then has a 4.0 times 10 to the power of 21 charge carriers per meter cube. So this is n, number of charge carrier, okay, per meter cube. And then when a current 0.0025 milliampere, so this is current flow. So also given in the diagram here, 0.0025 milliampere is passed through a pair of surfaces. So the pair is which one? These two pair. This is the pair of the surface where the current pass through. So this become a cross-sectional area for the current here pass through this cross-sectional area. Not this side. This is very important. Where is the cross-sectional area is? Okay, and then continue reading. And a uniform magnetic field of flux density B applied at right angle to another pair of surfaces shown in the diagram. So the B is downward here, at right angle. So means 90 degrees here with the surface of the semiconductor. So downward direction B. So applied at right angle to another pair of surfaces shown in the diagram. Then a potential difference of 60 millivolt develops between the third pair, of surfaces. So this is one pair, this is the second pair, the top one, the widest one, area, the largest area. So on side, the third pair is this side, okay. It gives you the potential difference 60 millivolts. So what can be understood from here? It is understood that this 60 millivolts is the Hall voltage. Okay, this 60 millivolt is the Hall voltage. So it's not the voltage across these two pair. The first pair mentioned. This is the two pair area. Okay, this is the first pair area. So it's not the voltage across these two, but the voltage across the third pair, this pair. So it is understood that this is the Hall voltage. Okay, 60 millivolt is the Hall voltage. So you must very, very careful. Hall voltage is not the same as voltage across these 2 points, but it's across another 2 points here. Okay, mentioned in the diagram, mentioned in the question is the third pair. Must be very, very careful. What is the Hall voltage? Is across which pair, pair actually of the surfaces. Okay, now question A. Find the drift velocity of the charge carrier in the semiconductor. We are going to determine the V. And then B, find the magnetic flux density B. And then C, determine whether the charge carriers have a positive or a negative sign if the surface Mn is positively charged. In this case, we are going to determine it's the N type of the P type actually, the semiconductor. Okay, so that was the C question mean. Okay, D, explain why semiconductors rather than metals are often used as Hall probes. Why choose semiconductor, not metal, used as a Hall probes? Okay, so let's try A question now. Okay, any one of you can answer the A question. Those who can answer can write there in the chat box. I think, okay, it's actually almost time, but I go through now lah. I go directly the answer, okay, because the time is too fast, flies too fast. So we discuss here lah. Okay, for A question we use I never. Okay, so V equals to I per NEA, and then we substitute the current given here 0.025 milli convert to meter. Number of charge density here given 4 times 10 to the power of 21. Electron 1.6 times 10 to the negative 19. The charge for if this is the P type or N type is still the same. The charge is because it's the current flow here is flow of charge hole and electron is still the same 1.6 times 10 to the power of negative 19. And finally the area. Okay, choose this area where the current flow. So refer to the diagram here, the current flow this way. So this we choose this cross-sectional area. So means 3 times 1 convert to meter. 3 millimeter times 1 millimeter. So you calculate, you get V equals to 1.3 times 10 to the power negative 3. Okay, we put here because we're going to use this in B question. Find the magnetic flux density. Okay, next we are going to find the magnetic flux density. Okay, so we use BI per NET. So B equals to VH NET per I. Now we arrange the equation because we are going to determine the B, right? Okay, so we substitute the Hall voltage mentioned here, 60 millivolt convert to volt. Okay, and here, okay, then E, thickness is 1 millimeter convert to meter, and the current. So you get 15.4 Tesla. Okay. So Cikgu Non help me here. Okay, so the answer just now is 5.21 times 10 to the power of 21. Okay, thank you Cikgu Non. Okay, but the substitution is correct. Yes, only the answer. So you just change the answer. So you all got correct answer. Very good. Okay. Okay, so thank you Cikgu Non helping me here. Okay, so go back to the question. B is 15.4 Tesla. 15.4 Tesla. So the magnetic field are done for B. Then we go to C. We go to C. Determine whether the charge carrier have a positive or the negative sign if the surface Mn is positively charged. Okay, you are given here one side is positively charged. Okay, I erase this. Okay, this is given. One side is positive charge. Positively charged. So what should be the other side? Okay, so we apply Fleming's left-hand rule. Okay, apply Fleming's left-hand rule. So the B is downward. The B is downward. Okay, and then your forefinger points downward, and then the current this way. Okay, current let's say to the right, and the force, magnetic force is this way, right? Magnetic force is this way. So what happened is electron. So this is positive. So that's mean what happened? This side is negatively charged, right? Negatively charged. So therefore, the current charge carrier is the free electron because this is negative charge. So the negative will accumulate on this side. Okay, because given here is positive charge. So that's mean electron will accumulate on this side. So therefore, the charge carrier for this semiconductor is electrons. Okay, the free electrons. So that's mean the semiconductor used here is the N-type semiconductor. Okay, but the question doesn't mention what type. So it just asks you to determine what is the charge carrier. So you can just say electron. Okay, if the question asks for what type of the semiconductor, you can say as N types. Okay, okay, done for C. Okay, then we go to D. Finally, D. Explain why semiconductors rather than metals are often used as Hall probes. Why we use semiconductor? Okay, this one refer to the formula. Hall voltage is equals to BI per NET. Okay, so if B is constant, I is constant, E constant, T constant, refer to the N. N is a number of charge carrier. So Hall voltage is inversely proportional to N, number of charge carrier. Yeah, N is number of charge carrier, density, number of charge carrier density, or number of charge carrier per unit volume. So for metallic, N is very large. This is inversely proportional. So if N is very large, so that means VH is too small to be measured. Okay. So therefore, it's better to use semiconductor. For semiconductor, N is comparatively smaller. So therefore, when N if refer to the equation here, smaller N give you higher Hall voltage. Higher Hall voltage. So therefore, a Hall voltage is large enough to be measured. That's why semiconductor is rather used than metals as a Hall probes. Okay, so that's all for today's topic, Hall effect. So you've able already to describe the Hall effect. Hopefully, so if you still cannot, you can do revision by referring back to this live, this live as a video. Okay. I give back to our moderator, Teacher Ayu. Okay, Teacher Ayu.
Okey, terima kasih. Terima kasih diucapkan kepada Madam Rosmaya atas perkongsian ilmu yang sangat bermanfaat, mudah difahami dan sangat menarik ini. Okey, alhamdulillah kita dah selesai untuk kelas pada petang ini. Okey, tahniah diucapkan kepada semua yang setia mengikuti kelas pada petang ini dari awal hingga ke saat ini. Okey, sebelum kita tamatkan sesi siaran langsung hari ini, mohon tutup ruangan chat dan klik butang subscribe dan aktifkan ikon loceng supaya anda tidak terlepas sesi kelas yang seterusnya. Okey, sekiranya anda suka dengan apa yang dipelajari pada hari ini, okey, sila klik like dan share kepada rakan-rakan di media sosial, FB serta Insta anda untuk sebarkan ilmu dan beroleh kebaikan di atas perkongsian tersebut. Okey, sila type done di ruangan komen sebelum link sijil akan diberikan. Okey, sebagai tanda terima kasih daripada cikgu kerana kehebatan kamu semua menyertai kelas tuition percuma pada hari ini. Okey, kod yang terakhir, nombor kod yang terakhir kita ialah nombor 9. Okey, nombor 9. Okey. Okey, jadi anda semua sudah mendapat kelima-lima kod akses, nombor kod untuk tebus mata kredit. Link diberi di ruangan komen. Okey, pastikan anda mempunyai ID Junior e-didik untuk menebus mata kredit berkenaan. Okey, link sijil boleh didapatkan pada bahagian chat. Kod akses adalah hashtag kelas AYU e-didik. Okey, sila ambil perhatian. Link tersebut akan tamat tempoh setengah jam selepas live ini. Okey, pastikan anda guna email e-didik sahaja. Okey, sekali lagi saya ucapkan ribuan terima kasih kepada Madam Rosmaya dengan kelas petang ini yang amat menarik ini. Okey, tahniah juga diucapkan kepada anda semua yang setia bersama kelas pada petang ini dari awal hingga ke saat ini. Okey. Okey, jadi kelas seterusnya Untuk tuition fizik PELAJAR adalah pada waktu yang sama pada minggu hadapan, iaitu pada waktu yang sama macam hari ini juga, iaitu hari Ahad pukul 5 petang. Okey, anda semua dijemput untuk ke portal www.academyyoutuber.com untuk mendapatkan jadual tuition dan info terkini. Bantu cikgu untuk sebarkan kelas tuition percuma ini kepada rakan-rakan dan guru-guru seluruh Malaysia. Okay, usaha ini adalah hasil gabungan guru-guru seluruh Malaysia untuk semua para pelajar seluruh Malaysia, terutama dalam menghadapi saat genting melawat pandemik COVID-19 sekarang. Okey, semoga kita mendapat manfaat daripada kelas-kelas yang dijalankan. Ingat hashtag, okey, bermula percuma, selamanya percuma. Okey, insya-Allah. Okey, terima kasih kepada semua. Okay, segala yang baik itu datangnya daripada Allah dan jika terdapat sebarang kekurangan dan kelemahan itu adalah daripada kami. Okey, semoga kita bertemu lagi di lain siaran. Okey, Assalamualaikum dan selamat petang. Okey, bye-bye.
Bye.
Wow, banyaknya hadiah menarik menanti anda. Wah, kini Akademi YouTuber mengambil inisiatif baru di mana memberikan hadiah-hadiah ini secara percuma. Ya, percuma kepada anda semua. Bagaimana caranya? Dengan mengikuti kelas tuition online percuma Akademi YouTuber sambil mengutip mata kredit, anda dapat menukarkannya dengan hadiah-hadiah yang menarik ini. Tunggu apa lagi? Segalanya percuma. Jangan lepaskan peluang tau. Dah dapat banyak hadiah menarik, takkan nak lepaskan peluang. Layari www.academyyoutuber.com sekarang untuk maklumat lanjut.
Dibawakan kepada anda oleh Akademi YouTuber.